Dalton's partial pressures is basically going to be the mixture of all the gases put total at the sum of the total gases and put together as if they were acting alone. So basically it states for a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. So let's give you an example of Dalton's partial pressure with scuba tanks. So if I give you 100.8 grams of O2 and 289.8 grams of N2, they're pumped together into 6 liters of scuba tank that's kept at 20 degrees Celsius. What is the partial pressure of each gas? And find the total partial pressure in the tank. Alright, so for this type of equation, you first have to assume the fact that these gases, when they are being put in that same container, basically is going to be a sum of those gases. Second thing is, if you take a look at the gases that are in there, the first thing you want to figure out is what's the partial pressure of N2. So if I go ahead and figure out how many moles of the N2 I have, you find out that it has 10.34 moles of the N2. So divide the molar mass by 289, you get 10.34. Then what you want to do is find out what the pressure of nitrogen is. So by rearranging the PV nRT equation, you find out that Pn2 equals nRT over V. Once you plug that in, you're going to plug in your 10.34 moles of nitrogen plus the R constant times the 293 divided by 6, which gives you a pressure of 41.5. Now step 2 is we have to find the individual pressure of O2. So go ahead and pause the video if you need to, but the idea here is to figure out what that pressure is using the exact same method. So now what we do is we go ahead and take the 32 grams of the O2. Now remember your sig figs for this one. We're looking at 4 significant figures. 1 mole of O2 over 32. That gives you 3.150 of the moles of O2. You find your PO2, plug the 3.150 in and your RT value, and you should get a pressure of 12.6. And again, going along that same logic, we're going to go ahead and find the total pressure of the tank. So because we have these two gases, we're going to sum them. And so according to Dalton's partial pressure law, what you have is pressure of the total equals to 54.1 atm. So you're adding in the 41.5 from the nitrogen and 12.6 for the oxygen. Alright, so let's talk a little bit about mole fractions and what is a mole fraction regarding gases. So gases love to be in these mixtures or percent comp, what they call it. So if I get a bunch of gases, I put them in a tank and I want to know what exactly is the mole fraction, what I want to do is find out what the moles of one component in the mixture is divided by the sum of those mixtures. So let me give an example here. Let's say I take XA, and XA would indicate the mixture. Put in some Na in there, I add up all the moles, that should give me the mole fraction. Pretty straightforward in terms of percent comp. So let's take a look at the first example for a mole fraction. So it says find the mole fraction of each component in the gaseous solution that contains that of 6.7 moles of helium, 2.5 moles of argon, and 1.6 moles of Cl2. So very simple type of calculation. You're going to take helium 6.70 divided by the total of everything, which gives you 0.620, so that's about what, 62%. Then you take the mole fraction for argon, which is 2.50 moles of argon. You divide it by the total, which is 0.23, and it all should add up to 100. And you take the last one for chlorine, which is 1.60, add them up, you get 0.148. Once you do that, you're going to subtract the total, and then you should end up getting it. So anyway, so if you add them all up, you should get to 100. Alright, so here's another example of another mole fraction, and this one says you have a gas solutions containing Ne, H2, and helium, and the mole fractions of Ne and H2 are known to be 0.233, 0.478. What is the mole fraction of helium? Alright, so the first thing is, because the whole thing equals to 1, you do know that they're already giving you the mole fractions for helium and nitrogen, for hydrogen, and neon, and so you're going to add those up and then subtract it by 1. And so when you do that whole calculation, you should end up with 0.289. So mole fractions and partial pressures can also be used. So if I actually ask you what is the partial pressure of each component, you multiply the total pressure by its mole fraction. So in this case, we have 1 mole fraction. The mole fraction of O2 in the container is 0.97, and it's found to be 0.210. what is the partial pressure exerted by O2? So the first thing you want to do is what is given and what are they giving you and what do they expect you to find. So because they're giving you the mole fraction is 0.97 of that 0.210, the pressure is 0.970, 0.97 atm. What they're looking for is what is the impact of the O2 in the total container. So what we're going to do here is multiply your pressure total, which is your 0.97, multiplied by your 0.10. And so the answer here would be 0.20 atm. So pretty straightforward in terms of mole fractions and partial pressures. Now, this is an example of how do we collect gases. So on the experiment side, if I ask you, I want to figure out how much gas is being produced in a substance or in a mixture, what I need to do is I have to collect the gas somehow using some sort of tubing. So if I take a look at hydrogen peroxide and I add NaClO aqueous solution, it's going to release water and an O2 gas. And so if you take a look at this example here, salt's being produced, water's being produced in O2. In step one, I invert a graduate cylinder and I measure how much gas is inside, right? I put the reaction inside this vessel. The O2 is going to pump out through this tube here, and it's going to get pumped into the side. And the gas that's being trapped inside will actually tell me how much gas is inside this container. So if I want to know how much gas is being produced, what I would do is measure that distance, that amount of volume that's being occupied there. Now, another way to measure collecting gases over water obviously has to do with this idea of your atmospheric pressure. So when measuring the volume of gas collected, you first must first line up the water levels inside and outside the graduate cylinder. So we'll be doing an experiment about this and try to figure out how to measure gases. And this ensures that the pressure inside the cylinder is equal to the atmospheric pressure. So as an example, if I ask you right now is what is the atmospheric pressure out here, it's going to equal to the O2 plus the pressure of the water. Because remember, there's a little bit of pressure coming out from the water that's allowing the water to go up. And so what you need to do is take into account both the O2 being produced and also the pressure of the vapors of the water going up, or the pressure of the atmosphere. So here's an example of collecting gases over water. So 0.129 sample of an unknown gas was collected over water at 25 and 1 atm. So the collection cylinder contained 37.45 milliliters of gas after the sample was released. But the vapor pressure of water is 23.76 millimeters of mercury at 25. So again, the reason why we have to take into account this vapor pressure is because, again, if you take a look at your total, you have to take into account that pressure for water if you're inverting in that cylinder. So the first question is, what is the molar mass of that unknown gas? So the first step is to convert the units to atmospheric pressure. So if I take a look at your pressure, which is your water, it's 23.76 millimeters of mercury. We have 3.126 times 10 to the negative 2 atm. The second thing is we want to find the partial pressure of the unknown gas. In order to do that, we're going to have to go back to our equation of what our P total is. So it's going to be our pressure over the unknown plus pressure of the water vapor. And in order to find that, we're going to have to subtract the water vapor from the pressure of the total. So if I take the total 1 atm minus 3.126, you get an unknown pressure of 0.98 atm. And next step is you want to find out what's the moles of the unknown gas. So given our pressure of our unknown gas, the volume, the R, and the temperature, we can figure out how many moles we're getting. And in that respect, we're going to get 1.5 times 10 to the negative 3 moles. Once we do that, we can figure out the molar mass of the unknown gas by dividing it, by getting our mass of our unknown divided by our N unknown. And so if you take a look at our mass of the unknown is 0.129 that we got earlier, divided by your moles, and your molar mass is 86 grams per mole. And so there we can identify exactly what type of gas we got based off that situation. So this is where it gets a little bit tricky, but it's a really interesting way of figuring out how much gas you have, and specifically these type of containers when you're looking at pressure of these unknown gases.